This is an introduction to exercise 6C on index laws 3 and the zero power. Again, to be very clear, you do not need to know the names of them. You don't need to know, label which one is index law 3 or prove that, etc. I just need you to know how to use them. So, for our June question, we're just using index laws 1 and 2, which is just your multiplication addition one. With the one on the left-hand side, we have a to the power 4 times a to the power 3 divided by a squared. Now, I want to remind you that when we do expressions like this and simplifying, BODMAS does come into play, but in this case, times and divide, same thing, so we just leave it in the order that it is. So we go a to the power 4 times a to the power 3, we rewrite that as a to the power of 4 plus 3, and I'm going to skip that step. I'm just going to put in the divided by a squared by writing minus 2 at the end of it. Welcome, take a seat. Do you have a lens? Thank you very much. So 4 plus 3 minus 2, so I'm skipping ahead, but if I really wanted to, I could write out the full steps by saying this, and then writing this, a to the power 4 plus 3, which we know is 7, minus the 2, gives us a to the power of 5. By the end of this topic, I'm hoping that you can just look at this and go, alright, well, a to the power 4 plus 3 minus 2, 5, done. That's it, you don't need to do anything else. Let's do the second question. Our second question is a little bit trickier. I always say treat the numbers first, ignore the letters or the pronumerals, ignore them, and we're just going to deal with the numbers. On the top I have 5 times 4. I know that's 20. So for now, I'm going to write 20. And on the bottom, I'm going to have 10. Because 5 times 4. And then I'm going to deal with the letters. On the top, I've got a squared times a. Again, we deal with one type of letter at a time. Don't try to deal with a squared, b cubed, and then etc. Just figure out a's, b's, etc. So a squared times a. What is the power of a when there is no power? Thank you very much. It is a 1. I'm going to make that distinction very clear. Not a 0, it is a 1. Just like 1 times x is the same as just writing x. So a squared times a to the power of 1 gives us a to the power of 3. I'm going to write it out in full steps. You do not need to write out the full steps. When you're actually doing your assessment, you can just jump straight to a to the power of 3. I don't mind. And then we have b to the power of 3 times b to the power of 2. So that's going to be b to the power of 3 plus 2. And I'm going to leave the bottom the same for now. ab cubed. Okay, let's start simplifying a little bit more. 20 and 10. 20 divided by 10. Easy. 2. So the 2 goes on the top. I have a to the power of 3 and b to the power of 5. And then bottom, I'm going to copy down exactly what I had before, except I've simplified out the 10. So I've got ab cubed. I want to be very clear, you are not expected to write out every single step I've written here. This is just while we're explaining and learning the laws. Later on, towards the end of the unit, you are welcome to jump straight from the first step here to the answer. Our answer being, because we are dividing a cubed by a, remembering the power is 1, it becomes 2, a to the power of 2, and b to the power of 2. I don't need that fraction, that vinculum, if anyone's interested in the name of the line. We don't need that anymore. It's just that, because you could, if you wanted to, you could write this. Same thing, doesn't matter. So 2 times a squared, b squared. That's it. Any questions? Easy. Okay, let's get into the stuff for today's lesson. I'll keep that on the screen for a little bit longer. Today we're trying to answer what happens if we have a different kind of power. The third law tells us that if we have a power to a power, we multiply. I'll highlight what I'd like you to write down. If we have a power to a power, we multiply. And a very basic example, I'll get you to write that one down too. I'll zoom in a very quick moment. So it's a to the power of m, all to the power of n is a to the power of mn. Alright, I'm hoping you've copied down the example on the right hand side if you needed it. There we go. A very brief example, x to the power of 2 to the power of 3 is x to the power of 2 times 3. Just don't get that mixed up with x to the power of 2 times x to the power of 3. That is a different scenario. That is your index law 1. Okay, the second one I'd like you to write down is your 0 power. This is very, very straightforward. Anything to the power of 0 is 1, except 0. I'm more than happy to show you the explanation for this. It is a very confusing concept to understand, and I'm not expecting you to know in year 9, but I won't go through that now. So a to the power of 0 equals to 1. Thank you very much. Now this note right here is important, but I won't get you to write it down. It's not important enough for me to get you to write it down. Because you're going to see this scenario where a does not equal to 0, sorry. So a is not 0. Alright. That means any number, it could be 0.000001 to the power of 0 is still 1. A billion to the power of 0 is still 1. That is a very straightforward one, and I'll give you a heads up. There are a couple of tricks. Because the law is so easy, there are a couple of tricks that I might, or in future, your teachers might try and get you to fall into. So let's start by looking at an example, and then at the very end I'll start answering the question, why does anything to the power of 0 equal to 1, if you're curious. Let's go through the example. Right here, we have x squared to the power of 3 times x to the power of 3 to the power of 5. Remember, if it's power to a power, we just multiply. So this one here is going to be equal to x to the power of 6. I am jumping that step. I'm not writing 2 times 3. I'm hoping that you're able to recognize that yourself. I'm going to leave that one separate and then write x to the power of 15. Because it's x to the power of 3 times by the 5. So here it's power to the power, so 2 to the power of 3, x to the power of 2 to the power of 3, sorry. So we have x to the power of 6, and then we have x to the power of 15 because it's x to the power of 3 to the power of 15. So to the power of 5. Gosh. A lot of students make the error of just adding those if they're power to a power. Please make sure you don't do that. And then this is the same question you've done from the last exercise. So it just becomes x to the power of 21. Add them together. Easy. Any questions? Okay. Next, we've got the same idea, but just with a slightly different rule. We've got m to the power of 3 times 4, or m to the power of 3 to the power of 4. So we've got m to the power of 12, and it's frozen. It should be m to the power of 12 over m to the power of 7. No, apologies, my laptop seems to be frozen. There we go. All right. M to the power of 12 over m to the power of 7. We simplify that. Same thing as usual. We've got 12 minus a 7, gives us m to the power of 5. If you're not sure what I mean by certain things, or if I've written this in a weird way, please let me know. My writing is not infallible. Okay. The last one looks very complicated. I promise it's very easy, but again, there is a trap that a lot of students fall into. I'm going to just look at the numerator. Don't look at the denominator, just look at the numerator. We've got 2 times y to the power of 0 and negative 3, minus, and then 3y all to the power of 0. One of these equals 1, and the other one does not. Which one equals to 1? Is it the 3y all to the power of 0 or the 2y to the power of 0? Which one of these equals 1? So I'm telling you, most students will look at them and say they both are 1 just because it's the power of 0. It is 3y. Yeah, absolutely. The reason is Because the first one's technically 2 times y to the power of 0, isn't it? So the first one, we rewrite it as 2 times y to the power of 0 is 1. So it's 2 times 1. That is 2, not 1. The second one, it's all of 3y to the power of 0. And all of 3y to the power of 0, regardless of what y is, it's going to equal to 1. Obviously assuming y is not 0, but we don't need to worry about that. Question? Rose? And the bottom, we're just going to leave that as is for now. 6x power 5. I'll make a very quick note. This is a prime opportunity for you to start writing your x's like I do in terms of it being curved. Because if you don't, this can easily look like times 6 times x times 15. It gets very confusing. So if you write your x's like this, writing x times x is going to look like this. Yeah, so just prime opportunity for you to start writing x's in prime numeral form. Alright, let's keep going. 2 times 1 is 2, minus the 1 is 1, so it becomes 1 over 6x to the power of 5, and we cannot simplify that any further. Okay, are there any questions about our practice problems? Alright, what I get you to do is I get you to start on exercise 6C when you're ready. But please stay quiet, because I'm going to go through, for those of you that are curious, why anything to the power of 0 is 1. Okay. So the question is, why does anything to the power of 0 equal 1? It doesn't feel like it makes sense. If it's anything to the power of 1, right? For example, if I said, let's say 2. 2 to the power of 1 equals 2. Anything to the power of 1 is that number itself. If I say 2 to the power of 2, that is equal to 4. 2 to the power of 3 equals 8. And every time we're getting bigger, it makes sense. But that gap between these numbers is different. If I have, for example, 2 to the power, sorry, not 2, let's say 6 to the power of 2 versus 6 to the power of 3, it wouldn't be a gap of 4. It wouldn't be a gap of 6, it'd be a much bigger gap. So why does it always equal to 1 if it's the power of 0? I'm going to keep going, and the reason I'm going to keep going is because it shows a pattern. Every time I increase the power, I'm multiplying by the number that I get. So, for example, 2 to the power of 3 to 2 to the power of 4. I'm just multiplying by 2. That's just what indices are. I'm multiplying by 2. That's how I know what 2 to the power of 6 is. It's just going to be 64 because I'm doubling it again. If I want to go backwards, I just divide it by 2. So, here I divide it by 2, and I can decrease the power by 1. Right? 60, it makes sense. 32 divided by 2 is 16. It works both ways. If I keep going here, divided by 2, it makes sense. The same thing applies. So if I go this way and divide it by 2, it's going to equal to 1, no matter what number that base is. If it's 16 to the power of 0, well, again, from 16 to the power of 1, which is just 16, you divide it by 16. No matter what you get, you would get 1. Now, here's the thing. If 2 to the power of 0 is 1, right, and we haven't learned this next law yet, but it's just an insight into it, could you figure out what 2 to the power of negative 1 is? You absolutely can. What would it be? No, because we're following the pattern. We're going divided by 2. If we go 2, we're dividing by 2 every time, right? Now, that's actually a bit of a trick. A lot of people see it being a negative and think the answer has to be negative. 1 divided by 2. We're just going backwards one more time. Let's get a half. It's a bit weird, isn't it? It all follows a pattern. I can go 2 to the power of negative 2. And that answer would be 1/4. I'm decreasing. I'm dividing. If I'm increasing my power, I multiply. If I decrease my power, I divide. Now, you don't need to know this. The laws are there so you don't have to memorize this. But this is the reasoning behind why anything to the power of 0 is 1. And later on, when we do negative powers, why we get a positive fraction instead of a negative number if it's got a negative power. Okay.